Oh, hello, welcome back to tchdy Live. It's a show where I am learning the latest or interesting things in the world of tech, either to improve myself as an IT professional or in order to just be entertained and learn something new and something fun. There's my trusty tablet here. If you follow my videos, I usually use it for writing the notes and things that I want to remember, things I find interesting. Basically, a note-taking app. So if I run this service that I created, I should have my tablet up and running somewhere around now. Yes. You're surprised. If anyone is watching my videos, you might be surprised because I changed my wallpaper. I had this pretty cool pink-haired girl with horns and a Sega shirt. It had a cartoony vibe. You can watch it in some of my older videos. And now I have this. I don't know what even is this? Is this like a rainforest type of thing? Some of these trees are pretty tall, pretty creepy as well. It almost looks prehistoric in a sense, even though there's a guy here meditating. Okay, that's not the point of these videos. Let's start the work. Let's start the grind. Okay, let me show you the code. I left you on a cliffhanger last time. This is all I wrote. I had to run quickly, so unfortunately I just imported the packages and I ditched. But now I'll continue and I'll show you as well. Where's the screen copy? Where's the screen copy? Ah, it's here. LC for launching. Let me just do a refresher on some of the concepts. Because we want to understand how all of this works under the hood, how it all fits together, and what's the pipeline for this. First of all, tchdy. I think I mentioned it last time. I did because here I have it written. tchdy is a search API. LangChain integrates tchdy, and I'm gonna write this because maybe that's important. As a search tool, it's an API, but integrates as a search tool. It's like Google search, but for agents. It lets your agent look up real-time information on the web. So it's external. Agent can call it when it decides it needs more information. And what we did, yeah, we imported tchdy search. I also created an environment variable as well. So it's hidden in the N file, but it's there. It's there. In order to use tchdy, I think there's a free tier that's relatively well equipped for what we need. What else? What else? What else? What else? So let me just write all of this. LLM is going to be chat open AI. I'll explain all of this. I mean, not that I'm an expert in anything, but I'll try to explain it as good as I understand it. Temperature of 0.3, streaming through the, this is actually a pretty interesting flag. It will print out tokens as they are generated, which is good for streaming. Callbacks, streaming. Wait, let me do this. Bum. Let's print out the tokens as they are generated. Let's set up our tool. Search tool, tchdy search, max results is 5. Prompt hub pull. I think some of this won't work because I will need to set up some more things. Let's see. Agent create React agent LLM tools search tool prompt. What else? We need an executor. Executor agent tools search tool verbose. Let's set to true. Let's create the main method. If name. What the hell? Is equals to what am I doing? Main. Oh no, I didn't want to run it yet. I don't want to run it just yet. Let's close this for now. Also, I don't want to run it from the integrated VS Code terminal. Print. Let's set it to a new line. Running the search agent. Query. No. Query is gonna be input. Ask me something to search. Response agent executor invoke. Input is gonna be the query, and then print the response output. So we created an agent in like what, 23 lines of code. Hopefully it will work. CD project, CD LangChain app. Let me move here. Main UV run python main.py. Okay, as I predicted, I need to generate a new OpenAI API key. Let me just do this. OpenAI platform. That's where I need to go. No, not. I don't want to see any docs, brother. I want to see the dashboard. API keys. Create new secret key. Let me just do some things off screen. It should work now. Let's see what happens. But it doesn't. It's most probably. I mean, it's the same issue here. OpenAI error. The API key client option will be set either by passing API key to or setting the OpenAI API key environment variable. What? Ah. Oh. I think I know what I did wrong. .tenv import loads.tenv, and before all of this I'm gonna do loads.tenv because I have some environment variables, brother, that are never loaded into the context. Let's see now. Ask me something to search. What is the weather in Paris right now? Huh? Ha 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 ha. Ooh, this is amazing. All right. Let me. I'm gonna explain everything. Everything as far as I understand. Again, I'm not an expert in this. I'm learning this shit as I go as well. If you came here to watch someone who knows a lot about this, well, you're not at the right place. But basically, what do we have here? Okay, I talked about Tavili. Already. The tool class. Where have here? I have the tool class. It's an interface, and this interface is wrapping any external capability, like an API. We are using Tavili right now. That's an external API. So the tool class is wrapping, in our case currently, this Tavili search, but it can wrap a function, a database query, anything, a calculator, an image generation service, another LLM, I hope. So every tool has a name, a description, and a callable function. And if I click here, will this work? So I clicked on the Tavili search class. Tool that queries the Tavili search API and gets back JSON. Setup. Install LangChain Tavili and set environment variable. I already did this. Okay, so we also have an example of the user right here. What happened at the last Wimbledon? This is the query. There are no follow-up questions. There's no answers. Here's the result. Andy Murray pulls out of the men's singles draw at his last Wimbledon. Blah, blah, blah. There's a response timer. And here, okay, so here are the Tavili search properties. Description. This is a Tavili description. It says a search engine optimized for comprehensive, accurate, and trusted results, useful for when you need to answer questions about current events. It's not only it not only retrieves URLs as snippets, but offers advanced search depths, domain management, time range filters, and image search. This tool delivers real-time, accurate, and citation-backed results. Inputs should be a search query. Execute a search query using the Tavili search API. So we have the query here. Some of these properties they're making me confused. I don't properly comprehend, but search depth. Okay, we have basic and advanced, include images. I could guess what some of these are doing. It returns a dictionary, string any, search results containing the query, which is the original search query, the results, which is the list of search results, each with title, URL, content, and score. API wrapper row results. So we have the query, include domains. All right, so this is like a big execution method right here. Check if the results are empty. You can use the tool asynchronously. Okay, all right. Now, I think I also have somewhere something cool. I'm gonna also explain what's Langsmith, and I should also write this so I don't forget it. Where's my tablet? It's here. And I'm gonna put it in bright red. Set up a Langsmith account. I will probably talk more about Langsmith in the video in which I set up a Langsmith account, but it's a platform where we can debug, trace, and see the analytics for our LLM apps. It helps us visualize steps, thoughts, and actions our agent is taking, tracing calls to LLM tools, retrievers, etc. We can benchmark different configuration. We can store replay runs for evaluation. It's helpful. It's helpful. It's like analytics for our LLM apps. What else do we have here that might be interesting? Probably this prompt that we pulled. So we have the LangChain Hub, and the LangChain Hub is a public library of prompt templates. And this specific prompt is designed for the React framework, the React framework which we are using right now to create our search agents. So if I search for this guy online, wait. If I search for this guy online, actually, when I run that line, that command, I am downloading basically this prompt, which is tested in multiple scenarios. And it says, all right, answer the following questions as best as you can. You have access to the following tools. We are going to provide a list of tools and use the following format. Question, the input question you must answer. Thought, you should always think about what to do. Action, the action to take, the one should be one of tool names. Action, input, the input to take the action, blah, blah, blah. And this is how we implement it. What's another thing that is new for me as well is create React agent. Create React agent is tying all of this together. Basically, we are building a React pipeline with this. So LLM is using the React prompt to reason, and we have the tools that we provided, and the tools that we provided here are, in our case, the tchdy search. So the tchdy search will basically become, how do I call it? Like an extension, like a module. If you ever watch these, if you've ever seen Matrix when they pull in that Kung Fu module in his head, so he learns, so Neo learns Kung Fu, basically the same thing. And then I wrap this agent into an agent executor. So what an agent executor is, it's a way to control. I also don't understand this best, but I think I'm getting at it. It controls the reasoning loop. It parses the action. It runs the tools. It feeds the results back to the LLM, and so on and so on and so on. For example, so let's say I'm asking my agent what is the latest research on, I don't know, electric cars, on solar farms, on floating solar farms. So I will have here, do this. So the user will ask a question. The user, they will ask something like, oh, floating solar farms. And the agent then does the following. It says, oh, I have a thought. Search the web. And then this is a thought, and it also runs an action. Action. Tavili search. And keep in mind, depending on the question, the action will be interpreted different. For example, if you say, what is the latest research on floating solar farm, it will say, 2025 floating solar farms research. And then the tool that we are using returns back results. And then what we have, the agent, the LLM, has an observation. Like, okay, we got 3. Why's my cat sneezing in the background? Hey! We got 3 papers, for example, and agent then has a thought saying, oh, summarize these papers. And then we have the final answer, which is a summarized, which is a concise summary on the topic that we searched for. Basically, again, let me also maybe draw infographics if I can. So I have LLM, which is my language model. LLM does reasoning. So LLM and again, I forgot. So the user actually has the input. User input the question. We can summarize the user input as the question. We can summarize LLM as the reasoning, as the brain, and it's gonna use the React prompt here, and it's gonna decide what to do next. Now, the prompt is also the personality of it, and because we are using the template structure, this will be the way the structure of the reasoning will look like. And then we have the tools. Or the modules, as Snell would call it. And then we have the agent. I think LLMs should be hitting the agent before the tools, and then the agent is hitting the tools. Right. And then we have the agent executor and the final output. All right, I like this. Oh, let me also explain the response that we gathered here. So this is our input. Ask me something to search. What is the weather in Paris right now? And this is the query. This will be the input for the agent. And LangChain will pass this to the agent executor, which initializes a new reasoning loop. Here we enter a new agent executor chain. I need to find the current weather conditions in Paris. And for that, I'm using tchdy search. And the action input current weather in Paris. I need to find the current weather conditions in Paris. So LLM, OpenAI, is reasoning based on the React prompt template. And the React template teaches us to follow the structure that is written in where is it? I think I have something. Here. Question, thought, action input, observation, etc. So the LLM is thinking. Where is the terminal? Here. Now we run the tool, we run tchdy search. And this is triggering the tchdy search tool. And this is what it retrieves. All of this data, a structured JSON. Where is the observation here? Do I have an observation? I think I should also have an observation. Okay, and then we have the reasoning and the final answer. I have found the current weather conditions in Paris. These are the current weather conditions in Paris. There's overcast with a northern wind. And the final answer is here. And the LLM has summarized the structured tchdy data into human language. And this is the final reasoning step. And the chain has finished, and we have the final response. Bam, bam. That's it. So we saw each token as it's streamed in real life. And this is great for, I'm showing this live, so I'm actually not showing this live. I'm gonna edit this later, but I'm showing it as it's doing the job. So it's cool. I should also, as I said, I should integrate Langsmith, maybe not now. Definitely something to think about. Let me close this. And I want to continue this, but I have a video that I would want to watch. It's unrelated to LangChain.
Sponsored by boot.dev. Learn backend web development through immersive. This video is sponsored by.
All right. No, cat, what are you doing? I have a beautiful cat. You beautiful thing. So this is the video I wanted to run.
By boot.dev. Learn backend web development through immersive, gamified experiences. Go to boot.dev and use code WONDER to get 25% off your first annual plan.
I used to love these gamified,
You're 23 years old.
Gamified experiences. I remember I had a productivity tool that, in a sense, was using elements from role-playing games into making you do your shit, like getting your life in order. It was really fun.
Years old. You just moved into a modest 2-bedroom apartment with a roommate, a neutral acquaintance you're splitting costs and responsibilities with. To ensure everything is fair and cordial, you both establish who does what in the apartment. When and who takes out the trash, cleans the floors and counters, does the dishes, and so on. You determine you'll each do the dishes once a week. You take Sunday, they take Wednesday. Soon, the first Sunday comes around, and, as planned, you do the dishes. Then, the first Wednesday comes, and your roommate does them. This continues for a couple of weeks. Then, on one Wednesday, after coming home late from work, you find the dishes piled up in the sink. You don't say anything. In your generous nature, you assume it's a one-off thing, and your roommate will just do them the next day. When that Sunday comes, however, the pile of dishes is twice as high, spilling out of the sink and onto the surrounding countertop. They never did them. You want to tell your roommate that they should do the dishes today, but they aren't home and haven't been all day. And so, you do them. This keeps things on schedule anyway. When the following Wednesday comes, your roommate does the dishes. All is well and back to normal. That is, until the following Wednesday, when again, late into the evening, you find the sink filled with dishes. You go to your roommate and ask what's going on. They assure you they will do them. You accept this. The next day, however, the dishes are still there, piled even higher. And then the next day, and the next day. You realize there's a problem.
This pisses me off.
When that Sunday comes, you wonder what you should do. Do the dishes, or leave the already giant pile to grow bigger? What precedent have you set? What precedent will you set? Can you reset things? What if you don't do the dishes, and then your roommate still doesn't do them? The kitchen will remain a constant mess. Alternatively, what if you do them, and soon, you're always doing them, every time? Who are you dealing with here, and how can you deal with them most effectively? You wonder what decision, based on what strategy.
I found myself multiple times in situations similar to these. I don't know, in university where you have been divided into groups and each group has to do, I don't know, a certain paper. And there are people who are not picking up their share of the work. And you come to a point where you think and you have all these scenarios in your head. It's like simplified version of chess where you think, oh, if I do this, if I just give these people the pass so they don't do anything, I'm picking up, so if they slack, I'm picking up more work. Or if I confront them, I'm gonna start most probably a verbal altercation with them. Or even if I confront them, maybe I feel bad because they have some personal issues. Or maybe I could go to the teacher, which is like to the professor, which is like the most extreme scenario. I go to the professor and say, I don't want this person in my group. Sometimes I was that person as well.
You should make. This is a version of a famous thought experiment in game theory known as the prisoner's dilemma, a situation where two people would be better off cooperating, but each person has some incentive to go against the other. In both not cooperating, however, both end up worse off. In this case, the individual incentive is not spending time doing the dishes. The outcome is either a messy kitchen and messy roommate situation, or a clean one. Broadly, game theory is the mathematical study of decision-making and strategies in situations where outcomes depend on others' choices. More specifically, it examines the nature and effects of how conflict and cooperation among rational decision-makers can lead to optimal or suboptimal payoffs. In essence, it is a science of strategy. In social situations, in business, in economics, and in politics, in every interaction, whether between as little as two people or as many as nations, decisions are constantly being made that affect everyone involved. As individuals and collectives, we each possess the power to not only change our own circumstances, but also the circumstances of others, of the world. These decisions and their outcomes can be as benign as who does the dishes in an apartment, to as critical as whether a country and its citizens survive. Game theory suggests that every decision made with a particular aim can, in principle, be represented and understood as a mathematical model. In other words, with a clear goal and defined constraints, a rationally right choice can always be.
I have thought about this at one point. I remember, I don't know if my brain just works like this, but I found myself in these multi-dimensional situations in which I put weights to certain outcomes, and these weights, I mean, I would do some calculations in my head. I think that's a bit autistic, but I would do it by feel, but I could definitely understand how they work and behave in my head.
Always be determined. More yet, an optimal strategy can be determined across multiple choices. And through various computer programs and simulations, researchers in the field of game theory have actually found a strategy or an approach and temperament that, under many conditions in society and nature, has proven to consistently be extremely effective. And surprising to many in the field, the strategy is profoundly simple. Even more compelling, it is hopeful. It is something that each of us can apply to our own lives. Before going any further, it's important to note that in the context of game theory, a game is not how we conventionally think of one, though it can also include traditional games. Rather, game simply refers to any interaction that occurs between multiple decision makers where the outcome and payoff of the interaction for each individual depends on the choices made by the others. This can include games like chess and poker, but it also includes nearly everything else. Of course, not literally everything, but all direct interactions that occur between individuals or groups that involve competition or cooperation where there is a mutually affected outcome. And this is almost everything. Importantly, however, game theory does delineate two types of interactions, or games: cooperative and non-cooperative. Cooperative game theory includes dynamics like players on the same sports team, roommates, in theory, business partnerships, as well as international alliances and trade agreements. In these cases, goals are shared, resources and information are often freely exchanged, and fairness and mutual benefit is both implied and actively pursued. Non-cooperative game theory, however, is far more prevalent in the world, and arguably much more interesting. In non-cooperative games, there are typically winners and losers, as players act independently in their own interests, making choices intentionally to benefit themselves, potentially at the expense of their opponents. This sort of non-cooperative dynamic in tension is often used and simplistically reproduced in game shows. For example, in the late 2000s British game show Golden Balls, two strangers would sit across from each other and decide whether they wanted to split or steal a large sum of money with the other person. Each person's choice directly affected whether either individual got any money and how much.
Oh, I watched some of these videos on YouTube and Instagram. Man, they were cringe. They were cringe, especially if someone like persuaded the other person to split the money and the other person is splitting it. It switched to the first guy, to the Joker, to the prankster, to the asshole, and he's stealing the money, man. I feel sorry for these people.
But neither would know the other's final choice until it was revealed and locked in. If both chose to split, they shared the money equally. If one chose to split and the other chose to steal, the one who chose to steal got all the money, and the other person got nothing. If both chose to steal, neither person got anything. In these sorts of one-off situations, where one can either split or steal, cooperate or defect, game theory shows us that there is a clear rational choice. What is known as the dominant strategy refers to a choice that provides a player with the best results no matter what the other player does, and this is always the most rational choice to make. The choice is not about what could lead to the best possible outcome, but about choosing for the best outcome no matter what the other person decides to do, since you have no control over that. And so, in Golden Balls, the most rational thing to do would be to always steal. This is because if one person splits, then the other person does better by stealing. If one person steals, again, the other person, in a sense, does better by stealing because they get the same amount as splitting, 0, but are not manipulated or exploited by the other person. Technically, this is what game theorists would call a weakly dominant strategy, since the literal payoff in this latter situation would be equal to splitting rather than better. Of course, however, life is not a game show. Interactions are almost never one-offs without lingering continued effects. Decisions are rarely as simple as splitting or stealing, and outcomes are rarely as simple as half, all, or 0. In real life, there is almost always a much greater interplay with time, repeated interactions, uncertainty, leverage, and resources. If someone does or doesn't do the dishes once, that game is not over. The relationship and space are and can be either benefited or strained moving forward. When a business smears or partners with another business, that game is not over. Retaliation or a growth in resources can and will likely follow. When a country attacks, retaliates, or allies with another, that game is not over. Wars can begin or end. Nations can begin or end. With all this in mind, what is the most effective decision-making strategy or approach in temperament and life in general? Is there one? In 1980, political scientist Robert Axelrod set out to test and answer.
I'm wondering why isn't game theory more well known? We only had, in relation to the game theory, I remember we only had an elective course in university. And I mostly found out about the concept of game theory from internet, from videos like this. And again, I know only what a layman would know, like the most basic things that can be summarized from a YouTube video.
Answer this very question. Using computer programs to model different decision-making strategies, Axelrod orchestrated an experiment. He had leading theorists from various disciplines and places around the world create and submit programs that would compete in a tournament of an iterated version of the prisoner's dilemma. The goal was to submit the best strategy and win. The rules of the tournament were simple. Each player or program played a single game against every other player, as well as a copy of itself. In each game, each player had the option to either cooperate with or defect against their opponent. If both players cooperated, they both received 3 points. If one cooperated and the other defected, the player who defected received 5 points, and the player who cooperated received 0. If both defected, both received 1 point. Each individual game contained 200 rounds. The player with the most points by the end of all the matchups in the tournament won. In total, 14 programs were submitted, and then Axelrod added one that defected or cooperated at random with a 50% probability each round. Most of the submitted strategies began with cooperation, while others began with early defections. Some players were complex and calculating, probing for weakness and then exploiting it, like a program called Grass Camp. Some mixed in random moves to utilize confusion and surprise, like a program called Joss. Others were far more straightforward. Together, the program spanned from what Axelrod referred to as simple and nice to cunning and nasty. After the tournament concluded, Axelrod, along with many other game theorists, found the results profoundly surprising. He ran the whole tournament again 5 times over to ensure the results were dependable and repeatable. Each time, the results were consistent, and the same winner emerged. A program called Tit for Tat, which is one of the simplest and most cooperative programs of all. To further elevate the complexity and better mirror real-world circumstances, Axelrod conducted a second tournament. This time, there was no defined number of total rounds per game. With it now being a random unknown number, players could no longer track and calibrate their decisions against a defined endgame, just like reality. This time, 62 program strategies were submitted, and again, Axelrod added one that was random. The results were very consistent to the first tournament. Again, Tit for Tat won. Axelrod
So eye for an eye, right?
and many other game theorists found this extremely surprising because the expectation was that the winning strategy would be either highly complex, highly competitive, or both. That is, cunning and nasty. And yet, Tit for Tat was generally simple, nice, and forgiving. In terms of specific gameplay, Tit for Tat always starts with cooperation. From there, it always copies its opponent's last move. And so, it continues to cooperate unless or until its opponent defects. At that point, Tit for Tat immediately defects back, and continues to do so unless or until its opponent cooperates again. As soon as its opponent cooperates again, Tit for Tat then forgives, or no longer accounts for previous moves, and returns to cooperating, unless or until its opponent defects. So on and so forth. Interestingly, the results of this strategy equated to tit for tat never winning any individual games, since one-on-one it can only lose or draw. But across all matchups and games, it cooperated with enough other players to consistently end up with the highest score overall and win the tournament. Axelrod writes, in The Evolution of Cooperation, what accounts for tit for tat's robust success is its combination of being nice, retaliatory, forgiving, and clear. Its niceness prevents it from getting.
So, if I understood this correctly, it never won any individual matchups. It only could draw or lose. But across all the competitions, it was the best performing one.
From getting into unnecessary trouble. Its retaliation discourages the other side from persisting whenever defection is tried. Its forgiveness helps restore mutual cooperation, and its clarity makes it intelligible to the other player, thereby eliciting long-term cooperation. Moreover, almost all top-performing players in the tournaments shared in these similar qualities. And in later simulations, with even more realistic chaotic conditions, a more generous version of tit for tat that occasionally forgave defections instead of reciprocating them proved to be even more effective. Nasty players, on the other hand, seem to often find themselves in defecting wars that led to mutual destruction. Axelrod says, what makes it possible for cooperation to emerge is the fact that the players might meet again. The takeaway from this is reasonably clear. In continued, non-cooperative competitive interactions, like these tournaments, it is often beneficial to, at the very least, try to be nice. To lead with niceness and cooperation. This is not a weakness, but a strength. Conversely, an individual who often leads with or incites defection is more likely to weaken itself.
This is actually a fairly great observation. The problem with applying game theory knowledge to everyday life is assuming you're dealing with rational agents. The best strategy in life is to be forgiving, kind, and clear to start. If they do not comply, still be clear with them and give them a negative outcome to teach them to do the right thing with time. But hey, that's just a theory. A game. Fuck you.
And lose over time, even if it initially appears as if they are winning. Moreover, holding grudges is a weakness. Forgiveness is a strength. Of course, however, weakness itself is a weakness. That is, letting someone do you wrong without consequence will lead to being taken advantage of and losing. One's approach to exacting consequence is also important. It must be relatively equal, consistent, and clear, not opaque and manipulative. From a moral and historical perspective, the winning tit-for-tat strategy essentially mirrors an eye for an eye ethos. That is, justice and punishment should be proportional to the harm caused by an offense, but after proportional consequence, balance and cooperation can and should be restored. On a more individual level, it essentially equates to being kind, forthright, and understanding, but never a pushover. Of course, there are problems and limitations, both with Axelrod's experiment as well as game theory in general. Programs, simulations, and theories can arguably never truly reproduce, model, or assess the true scale and complexity of real-world interactions. Real interactions often involve many people and many issues, many perspectives, many goals, shifting ideas and opportunities, asymmetric leverage and resources, known and unknown information, vast errors and chaos. And perhaps most importantly, they involve the very emotional, sentimental, spiteful, and irrational nature of the human mind. As humans, we feel and hope and believe at least as much as, if not more, than we assess, calculate, and execute. Ultimately, however, game theory teaches us many important things. Perhaps one of the most important being is that every interaction in game is not always about winning. A strategy always focused on winning can actually be the least effective at winning overall, whereas one less focused on always winning can, over the long term, win. If we want to truly be successful across various areas of life, there are going to be, need to be, many instances of draws and losses. But so long as we continue forward with each new moment and each new interaction, open and willing to try again, ensuring we stand up for ourselves and hold true to our values, while striving to meet and unite with the world around us, we can steadily and surely move toward bigger, more important wins. Wins of cooperation, kindness, and mutual benefit. We can never truly know or control if people will cooperate or defect with us, but we can know and control if we will and why. And we can know that each decision we make will likely influence the nature and outcome of all the games in which we participate, present and future, potentially making or breaking
For 10 times
relationships,
more energy,
goals,
close your
systems,
open loops.
or even society
Here's why
and
this
planet.
matters.
And so,
Unfinished
at least for
tasks.
starters, for our own sake, when our day comes, let's be sure we do the dishes.
Yeah.
Games are a fundamental aspect of all of life. And so, naturally, our brains are wired to often treat and make sense of things through gamification. It is how we effectively build, understand, and improve. That's why this video's sponsor, boot.dev, is such an amazing fit for this video, and such an incredible SQL to boot.dev and use.
Alright, I would like to know more about it, but let me also do another video, which
No matter how small, drain mental.
as soon as I saw his vest, I said to myself, I need to watch this. Also, I have trouble with my energy levels. So...
Energy you could be focusing elsewhere. Here are some examples of open loops. The bill you haven't paid yet, the decision still unmade, that attractive person's number you haven't asked for, the article not published, the relationship you haven't ended, the room still uncleaned, the message not sent, the friend you said you'd call soon, or the boundary you need to set but keep sidestepping. Or Lewis's favourite one recently, the email you still haven't sent to the government. Open loops need energy to survive, but the upside for you is closing them releases energy. Here's why. In the early 1900s, the Gestalt psychologist Kurt Lewin realised something at a restaurant. He observed, waiters tend to remember unpaid orders better than paid ones. Fascinated by this, Kurt Lewin then relayed these observations to his graduate student Bluma Zygarnik, who did some research of her own, and she found this doesn't just apply to waiters, it applies to all of us. Then the term was coined the Zygarnik effect, to refer to the phenomenon of how we remember incomplete tasks better than completed ones, and this incompletion causes mental tension until the task is closed. So the key takeaway here is, of course, close the loop and reclaim the energy, because there won't be any more mental tension for you to direct energy towards. Just imagine where you can redirect this new reclaimed energy towards in your life. You can spend more time enjoying life instead of worrying, being more present in your conversations, working harder, being happier, or building more confidence. So before we cover what you need to do next, let's consider what modern science has to say about this. Putting things off doesn't protect you. It's stress.
But I love how there's like an extra couple of seconds of him erasing the whiteboard, which is fun. I feel like I'm listening to a university class.
In one study, participants were given the option to have a strong electric shock now or a mild one later. The results? 70% of the people wanted the strong shock now. Their reasoning? Well, they just wanted to get it over with. The deeper explanation? Prolonged uncertainty hurts more than immediate discomfort. As the saying goes, bad news is better than no news. But, of course, you don't always act like the participants in the study, because when you're overwhelmed, you avoid making a decision. Me very much included in that, even though I'm using the pronoun you. But a decision is all that's required for you to regain control and close your loops. So, here's what to do next. First of all, admit you have open loops. Then write them all down on a piece of paper or on your phone notes. You might write down 3, 17, 537. It doesn't matter how many you write down. Bullet point them. Then pick one. I suggest picking the scariest one on your list and starting with that. As the saying goes, run to trouble. Then be specific, not fuzzy. Complete the sentence. I will. Action. At. Time and place. The action is whatever this open loop needs you to do in order to close it. And the reason being specific is important is because if you're not specific, your brain won't know what to do and therefore you won't act. Then do it now or schedule it. But if you're scheduling it and then the time comes, do it. Do not negotiate with your emotions. Stick to the plan. This is your future self you're doing it for. Bring on the challenge. Then repeat this process for closing all of your other loops. But you'll notice, when the time comes to close your other loops, you'll do so with more confidence in yourself and with an abundance of energy. Sorry, messed that bit up.
I love him. I love him.
And helps you close another and another. You get the point. But oops, when you're in the trenches and the loop you're trying to close seems daunting, scary, and too overwhelming, remember this story. One day, a man and his son were driving home, but they broke down on a pitch-black motorway, so they had to leave the car and search for a phone dock in the distance in order to call a mechanic and ask for help. So the son grabbed a torch from the car and tried to shine it into the pitch-black darkness as his dad walked off in front of him, but he said in frustration, "Dad, this is useless, I can't even see anything with this thing." So, tired and now very fed up, the son just wanted to go home. But then he saw his dad walk towards him, now coming out of the darkness, and the dad lightly grabbed the torch and shone it in front of him on the floor and said, "You don't need to see a mile up the road, just 1 foot in front of the other. So long as you see enough to do that, you'll be okay." So the bottom line is, you don't need to fix your whole life. Just close one loop at a time. In other words, in order to forget the bigger picture, look at everything close up. Close the loop, reclaim the energy, or be tormented endlessly.
Love it.
So before we sign off, you might be thinking, Lewis, this is great, and I understand the importance of closing loops now, but loops never seem to end. Every week there seems to be new open loops that I have to close. Is this just the fate of my life? Well, here's a quote that might help you think about it differently. For a long time, it seemed to me that life was about to begin. Real life. But there was always some obstacle in the way. Something to be got through first, some unfinished business, time still to be served, a debt to be paid. Then life would begin. At last it dawned on me that these obstacles were my life. Thank you very much for your time and attention. Stay disciplined, playful, and dangerous. Adios.
This was all aimed at me, wasn't it?
What?
All this stuff.
What stuff?
The debt's not paid, the number's not asked for, the admin... Oh, hold on.
Amazing. I love this. I love this. I'm gonna start implementing this in my life. Now, I think we already mentioned a pretty often used concept, and that is the definition of a process, which is an instance of a running program. It's identified by a PID. PID is also known as process ID. Let me move this here. We can use commands such as ps or top to tell us what is running. Again, they serve different purposes. What I had actually now is I had a spike. in my CPU work. I noticed that while I was streaming, my computer became a bit laggy and patchy and it worked slower. So when I run top, I'll see a system summary on uptime, on load average, CPU breakdown, memory stats, and also the process list will show us every running process sorted by CPU usage. And this is the pulse of the Linux system. This is how you put your fingers on the heartbeat. And let's try to explain some of these lines here. This is the current system time. I know this because in 27 minutes I should hit the gym. So I have around 30 minutes of streaming, hopefully. 7 minutes is the system uptime, which is the time since the last boot, which again I had some lags, so I did this on purpose. I rebooted my system so that's why I'm up only 1 minute. Only one user is currently logged in. These numbers could also include SSH users, GUI, and other things. What is the load? Yeah, this is the load average. Let me do this again. Okay, I didn't need to. Actually, I should do exit. No, I shouldn't have exited. So top. So this is the system load of average over 1 minute, over 5 minutes, and over 15 minutes. Again, I would love. Unfortunately, I didn't run top when my PC was, when my computer was lagging. I would love to see the stats back then. But alright. But this is not CPU usage, it's the average number of runnable or waiting processes. This is the number of processes that are ready or waiting in the last minute, in the last 5 minutes, and in the last 15 minutes. So depending on the amount of cores, if you have only 1 core system, a load of 1 is full utilization. On a 4-core system, a load of 4 is fully loaded, full utilization. If I have, I think I have a 16-core CPU. Which means that, it's barely doing anything. Now, the second line here is the number of tasks running, or the task summary row, where I have the total amount of tasks, the amount of currently active tasks on the CPU, the number of them which are sleeping. There's a lot of them sleeping. Basically, a lot of them are sleeping because most processes sleep while idle or waiting for input-output. 0 stopped, 0 zombies stopped. Processes are suspended via a stopping signal. And zombie processes are defunct processes. So if you have here 400 sleeping processes, that's not bad, because most well-behaved Linux processes are actually sleeping when idle. What's here? CPUs. Now, each abbreviation is a CPU state. US is the user space, which means that this is a time running non-kernel code, or our apps. Basically 3% of my CPU is used by my apps. This is the kernel code, which means that 1.2% is spent in kernel mode. These are the processes with adjusted priority. We don't have any here. Idle system, there are 95% of idle systems. Which, again, as we already mentioned, there is a correlation between this value and this value. This 95% of a system is actually relaxed. Nothing is waiting for this core network. These are the hardware interrupts, non-significant. These are the software interrupts. We don't have any. Steal time, we don't have any. Again, our CPU is 95% idle. Our system isn't under any computational load. Memory usage. As you can see, I have 64 gigabytes of physical RAM. I have 54 gigabytes of unused RAM, which is not allocated. What's that? Around 5.7 gigabytes, which are actively used. And these are used as disk cache. The next line. This is the total amount of swap space, 4 gigabytes. Unused swap space is here. This is currently used, and this is how much RAM is really available before swapping will begin. Basically, swapping space is the emergency RAM extension on disk. It's slower than RAM, but prevents crashes when memory fills up. As you can notice, I don't use any swap space. My system is basically pretty idle, pretty healthy, even though I'm running OBS, even though I'm running the screen copy in the background. It handles that load pretty decently, not gonna lie. Yeah, let's also break down at least a row in the process list section. This is the process ID. This is the user that owns that process. This is the priority. 20 is the normal default priority. Lower number means higher priority. This is the nice value, which is the user space adjustable priority modifier. Virtual memory size is this value right here. Is the total memory the process can access, including shared libraries, files, and swap. This is the resident memory, which is the actual RAM currently used by the processes in kilobytes. This is the shared memory, which is the part of residential memory that's shared with other processes. What's this? This is the state. Our state is currently sleeping. How is he sleeping if I'm actually right now actively running screen recording? Okay. This value is of the percentage of CPU usage since last refresh. I assume this only takes into account one CPU because in OBS I have my CPU usage is 2.2%. So I assume this is only one CPU usage. This is the percentage of total memory of total physical memory that's being used. So where's my Brave? Here's my Brave. browser. Is it actively running? Where's Brave again? Oh, if I open a new tab, will something happen here? Yeah. So I have, if I start typing in my browser, but will it hit the running state again? Basically Brave, I don't see it here, but it's using around 1%, maybe even more of my CPU, and around 0.6% of RAM. OBS Studio is actually using a lot of CPU processing power, which again, I'm not sure why it's in sleeping mode if I'm screen recording right now, but all right. Okay, let me exit this. No, there's also, I don't have htop. Do I have no? Do I have htop? No. Both of them are just bonus tools on top of top, and they add, I don't know, some colors, maybe mouse friendliness. You can sort by using your mouse. They are scrollable. There's some easier filtering on them. Now, another interesting command is lsof, which lists open files. Basically, in Unix, everything is a file. We have regular files, directories, sockets, pipes, even devices. So basically, if we would type this, we will basically show what each process has opened, like files, ports, devices, libraries, things like that. Can I scroll this wider? Okay, here we have it. So we have command, process ID, I don't know what these do, user, which is the process owner. This is the file descriptor. This is type. This is a device, file size or offset, the node name, and so on and so on. So if you can see here, there are some common file descriptor abbreviation. There is tchdy, which is the current working directory. This is the root directory. This is the executable binary or script, and the rest of them are memory mapped libraries. So this command outputs a lot of data. So basically, we would mostly use it with a lot of filters. So we usually run it with a lot of filters. For example, let me just do this. Top OBS 4278 sudo lsof 4278 4271. And with this command, we can actually show open files that we run for this specific process, which is OBS. Or we can show what process is using a specific file, or what process is using a port. basically LSOP reads kernel data structures under processes, and that's why it's dependent on kernel APIs. Now, like, wait. Let's say I'm interested in finding what process is using too much memory, right? So if I do top and then I press uppercase M, if I press uppercase M, I'm actually sorting by memory usage. So the process at the top is actually the one consuming the most memory. Isn't this the antivirus? Wait, let me also do this. Q, let me leave this. Is aux sort mem head and then. Yeah, it's still this guy. What else is interesting and reproducible? For example, how could I determine which process is listening on a certain port? Let's say I'm interested in seeing if anything is running on 8080 or 4271. I think that's where my OBS is running. So I'm going to type in sudo lso files 8080. I don't know. I don't think I have anything here, but 4271 should be the port where my OBS is open. No, what? 4271. 6183. 6183. Why? Why don't I see anything here? I'm an idiot. I'm an idiot. This is the process ID. This is the process ID. I could actually search. This is searching by process ID, and this is searching by sorry, that was searching by port, and this is searching by 4271 by process ID. Okay. Oh, I need to run. Guys. I will be back. I will continue doing this. Thank you and see you. Bye bye. Let's move away from our process level view and let's talk about networks. I'll just put it here as a subsection. So there's in the book, there's a figure that looks something like this. There's a cloud, and this is the internet. Here we have the router. And then this is LAN. And then we have host A. Host B. And host C. So what do I have here? I have LAN, which is short for local area network, which is a small private network. It can be either wired or wireless. So hosts, which are these three connected to our LAN, are on the same subnet, meaning they can communicate directly. For example, they can communicate on the same IP and X. And this is controlled by a router. Now, our router right here is a special host that has two interfaces, one to the LAN, which is private, and one to the internet, which is the public side. And router is performing routing, moving packets between networks. It's also performing network address translation, which converts private IP to public ones. And it also filters traffics, something called firewalling. Now, the router is uplinking to the larger internet. It connects multiple LANs together through ISPs in everyday terms. So our router is like our local post office, and these LAN hosts are the people in our town, and the internet is the rest of the world, and the router reads each letter and sends it right way. Now, how is data moving in the internet? It can be explained by a simple concept, and that concept is a packet. The packet is the smallest unit of data transmitted across a network. And every packet contains two parts. A header and a payload. The header is containing metadata, who sent the package, or who should receive it, which protocol is the packet using, and more. And payload contains the actual data, JSON objects, part of an HTML page, a chat message, and etc, etc, etc. And why we use packets? We are using them because you can send pieces of data independently. It's easier to detect errors, and it allows multiplexing. Many apps can share the same link, since packets can interleave. So what happens is when we load a web page, there is not one giant blob of data. I go here, here, and let's say this is a web page. It's not one giant blob of data. We get multiple smaller packets like HTTP, GET, index.html or http get data or http get styles, and so on and so on. Oh, this is also something that I don't remember learning. I mean, I do remember learning. I don't remember retaining this information. That is the network stack or the layered model. So the book says there are 4 layers, even though I remember 7, but we'll do it one by one. So what do? We have application layer. Then we have the transport layer. Again, I think there are more layers in a 7-layer representation of it. This is the simplified one, I assume. All right, now let's go layer by layer. Let's explain it. So what do we mean when we talk about the application layer? So the application layer runs in our apps. Or something called the user space. It defines how programs communicate. All right, so in case of web browsers, they would communicate using HTTP. In case of email clients, they would communicate using SMTP or IMAP. Secure connections, we would have TSL wraps around them. We would use HTTPS. Okay, what about the transport layer? What about the transport layer? So transport layer is used in the kernel. So it defines how data gets sent. So we have TCP, which is a transmission control protocol. It's used by most applications, handles retransmissions, acknowledgements, and packet reassembly. And we have UDP, which is the user diagram protocol. Now, internet layer, again, this one also runs in the kernel. It defines how to get packets from one host to another across networks. Handles routing and assigns addresses. And lastly, we have physical or link layer. There we have examples such as Wi-Fi, Ethernet, and it defines how bits actually travel. So how is data moving between layers? Let's say we have a situation where host A is sending a message to host B. So host A is sending a message to host B. First thing that happens inside host A is that the browser sends an HTTP request in the application layer. Then the operating system drops it into a TCP segment, which is a transport layer. Then they add an IP header for the internet layer. Then they add Ethernet framing for the link layer, and then they send an electrical or wireless signal. Now on host B, the signal is received, and the HTTP server receives full requests in the application layer. Now, I want to know more about the transport layer. So we have two protocols here. There is TCP, which is a transmission control protocol. It's reliable, ordered, and connected. So how does it work? It provides a stream of bytes between two endpoints that guarantees data arrives in order, no duplicates, retransmission of packet loss, flow control, and congestion control. That guarantees, so all of these could be summed up or summarized as reliable. So it guarantees I haven't. So reliability. So the connection setup, it works in a three-way handshake. I remember this. I remember this. Basically, we go between the client and the server. And we have the SYN, which I assume means synchronize. And then server sends back a response in the form of a synchronize acknowledgement. And then client sends a message to the server with an acknowledgement. So TCP is used in HTTP and HTTPS as part of web browsing. It's used in SSH as a secure shell, file transfer protocols, and SMTPs as well. And what are UDPs? So UDP is fast, lightweight, and connectionless. It sends independent diagrams. So there's no connection, there's no guarantee. Where is it being used? In DNS domain lookups.